today we're going to talk about the energetics of vaporization and fusion. So just as a reminder, vaporization would be the process of going from a liquid to a gas, and fusion is the process of going from a liquid to a solid. All right, so we use the terms in terms of energetics for both the forward process and the reverse process. So vaporization energetics would refer to vaporization and condensation, and fusion would refer to melting and freezing. And so what we've been doing so far is looking at the heat required to change the temperature of a given substance, and we've been using the specific heat capacity for that. So that would be if we're in any of the parts of the curve that are that have a slope, a non-zero slope. So when it's a solid, or if it's a liquid, or it's a gas, and we're changing temperature. But hopefully you remember from honors that when we're changing state, we are also either using or releasing heat. And so even though the temperature doesn't change in that process, that also requires heat. So today we're going to talk about how you can calculate that change. So first, just two terms that you should know. The enthalpy of fusion is the amount of heat it takes to melt 1 gram of a substance, or 1 mole of a substance. Sometimes it's given in grams and sometimes in moles, at the melting point. So for water, that would be melting at 0 degrees. For the enthalpy of vaporization, this is the amount of heat required to vaporize 1 mole, or sometimes 1 gram, of a substance at the boiling point. So for water, that would be 100 degrees Celsius. Okay, so the practice problem here is how much energy is needed to melt a 10-gram ice cube and bring the water up to body temperature, which is 37 degrees Celsius, if you take it from the freezer, which is at -20, and put it in your mouth. So just a note, the heat of fusion here for ice is 0 degrees is 333 joules per gram. So that's a quantity that you would be given. You do not need to memorize that. It would have to be given to you in your problem. You would just need to know how to use it. And so in this case, we're given joules per gram. So sometimes it will be per mole. So you need to pay attention to your units. So first, let's do the temperature changes, or let's plot out how we would do this. So we start with 10 grams of solid water at -20 degrees. The first thing that we need to do is warm that up to 0 degrees. Sorry. So we'll use the Q equals mc sub s delta t that we've been using in the past for that transition. After we do that, we need to take that 10 grams of solid ice at 0 degrees and convert it to 10 grams of liquid water at 0 degrees. So there's no temperature change here, only a change in state. And then once we have all of the water in liquid form, then we need to heat it from 0 degrees up to 37 degrees Celsius. And again, that second change in temperature would be calculated using the Q equation that we've been using. All right, so just to go through this really quickly, so we're going to calculate 3 different numbers that we'll add together at the end. So for the first temperature change, we have 10 grams times the specific heat for ice is different than the specific heat for water, so make sure that you have the one for the right state. The specific heat for ice is 2.09 joules per gram degree Celsius, and our change in temperature is 20. It's warming up, so it should be positive. All right, let's do the second temperature change, since that is what we've been familiar with doing. So again, we have 10 grams. The specific heat capacity for liquid water is 4.18, and then our change in temperature is going to be positive 37 degrees because we're going from 0 to 37. Okay, and then the change in state is just a simple dimensional analysis problem. So the 333 joules per gram we could just use as a conversion factor. So 10 grams is what we have. If we do that times 333 joules over 1 gram, that will give us the heat for that. And so if you multiply all of these out and add them together, I'm not going to take the time to do all of that, you get 5,295 joules of energy is what's required to take that 10-gram ice cube at -20 degrees and bring it up to a temperature of 37 degrees in the liquid state.